All right, kia ora koutou. My name's Ross Stephen, and as Justin pointed out, I'm here in Avondale College in Auckland. So welcome to those all across the motu, and I'm just going to kick things off with the karakia, which is brought to you by Essens, our subject committee. So ki raro I te korowai kaitiaki o te kete nui a tānei, mā te hau e pupuhi te pā kahu kahu ki o mātou waka. Te kaha tānei, tangaroa, manakitia mai a tātou katoa, I roto I te hikoitanga I te ao rangi rawa ko papa, hei te oranga mātou, kia piki aki I o rawa Māui, kia toi mātou I o rawa mana, hui e, taiki e. And I'll just give a quick translation so you're aware of how this karakia connects to Earth and space science. And what it translates to is, beneath the protective cloak of the stars, may the wind blow new strength to our waka, and the strength of Tangaroa look after us all. As we navigate and journey the world of rangi and papa, from which our health is drawn, let us uplift their Māori, let us uphold their mana, and so it is. Welcome, and as Justin pointed out, please use the chat feature to let us know what questions you have as we go.
Okay, I'll just start by highlighting a few really good resources that we've used to develop this slideshow and webinar. So GeoTrips is something that Ross has actually shared with me recently. Ross, do you want to talk about GeoTrips?
Yeah, sure. I guess there's a lot of semi-professional geologists around the country, and GeoTrips is a fantastic way for people to record their own geological exploration. What you can see in the slide image there is, from zoomed out, clearly the Auckland region with the red hotspot there has a significant amount of information from your sort of amateur geologists. Great way to connect with your local geology if you don't know a lot about it. So jump on geotrips.org. I'm not sure. We've got that linked in the resources at the far end. And, it's got photos, it's got a bit of a geological background, and it'd be a prime place for you to find something local for you to do. Because one of the things we often see is people picking a context which is well away from where they are, and it, I guess, prevents the students connecting with it a little bit better. So I think a fabulous resource for us all to start to use. And if you find something yourself, you can always contribute to GeoTrips as well.
And the other two sources that we use, I use quite a lot in my teaching, is Tiara, which is the New Zealand Encyclopedia, and the Science Learning Hub. And they've got really good geology information and context that are a really good level for your kind of for high school students, really. So I'd certainly recommend using those. Also, of course, there's the Essens website. We've put a lot of time and effort into building a lot of resources in there. Starting with Jenny Pollock's been building a lot of stuff that is kind of the definitive resources for all the level 2 and 3 standards. And more recently, we've been doing stuff for the human-induced changes, and we're hoping to soon be doing some like Earth and space science context for the level 1 science standards as well. So they link to our Google Drive folder, so have a look in those, and there's heaps and heaps in there. I think you need to be a member to access those, so it's really easy to become a member. Just there's a membership form will be in this webinar when I send it out, and also you can just go to the Essens website and there's a membership form there, and then you'll be added to the Google Drive access permissions, and you'll be able to access all of those resources. It's also worth noting that this webinar and a lot of the resources that we've been producing are supported by the Network of Expertise, which is funding from the Ministry of Education to the subject associations, so we can spend time sort of supporting teachers and running sessions like this. So like we'd ask for your help to kind of help that funding going by, we've got a feedback form at the end, and just if ever you get the opportunity to say that you benefited from this, and hopefully that will keep the ministry supporting this funding and these PD resources.
I'll just point out too, membership for Essens at present is free, so it's not going to cost you or your department anything, and really encourage everybody to sign up. So, I mean, the title of the webinar was Te Reu a Māui, or about Zealandia. So we're exploring, I guess, the whole continent at the moment. And well, it's quite topical because it's quite a new thing, but a lot of geologists in New Zealand have been pushing for Zealandia to become globally recognised as an additional continent. So just going to briefly talk about what a continent actually is and follow along with that image in there as well. So we're a pretty small island nation here in New Zealand, but we have a lot of offshore continental crust present. And what's the New Zealand landmass actually is a small portion of that. And so a continent is characterized by having higher elevation than surrounding oceanic crust, which is quite frequently hidden away in the depths of the ocean. It's also containing a wide range of silica rocks. Justin will talk to a few of those, but good examples would be the Shirt across New Zealand, Shirts, and some limestones as well. Thicker crust and lower density than the oceanic crustal rocks, which are nearby and offshore New Zealand. And the final thing that constitutes what a continent is well-defined limits. So in New Zealand, as I'll get to soon, we certainly meet most of those criteria to be classified as a continent. Next slide, please, Justin. And throughout my conversation there, and I'd hope if we're teaching level 2 sciences, that would be at least aware of the difference in crust types present around New Zealand. And we've got, this is across the globe, sorry, but especially true here. We've got the continental crust, and we've also got oceanic crust. So a key idea linked to crust is that the chemical composition of it essentially determines the density of the crust, and this is how it moves around the planet with tectonic forcing. So our oceanic crust and submarine oceanic crust is typical of volcanic rocks. They're often rich in magnesium and iron, and you can see that in the image there where it refers to mafic rocks. So mafic being magnesium and felsic rocks. They've got a far greater density compared to the continental component, and as a result, it is generally drawn underneath the continent. Another key difference is the thickness of the rocks, and continental crust, because I guess it has a lack of recycling in the Earth's mantle due to, I guess, greater buoyancy with a lower density. It can build up to form huge, thick layers. And how those layers develop is, I guess, a key idea in teaching Earth science is the rock cycle. We get weathering and erosion events build up huge layers of sediment, and that can be over billions of years. Some of the oldest crust on Earth is dated to about 4 billion years old. So I guess around New Zealand, we've got a pretty unique plate boundary, and what it is essentially a bit of a twisted mess of oceanic and continental collision, as well as continental and continental crust collision. What that does, it leads Aotearoa to showcase extensively different geology across the Motu. As you can see now, te reo a Māui. I'm just going to refer back to the earlier slide and talk about how it does meet the criteria for being a continent. Justin, we can stay on that te reo a Māui one. So first of all, we talked about having higher elevation than the surrounding oceanic crust. And what you can see here, all of that grey area is essentially shallow sea, up to a depth of about maybe 200 meters. And it's big. In this particular image, it points out that a continent should have greater than 1 million square kilometers. This continent of Zealandia is 5 times that size. It's just that 94% of it is out of sight underwater. Another thing was that it has a broad range of rocks. New Zealand certainly does have that. We'll talk a little bit more about that soon. And a clearly defined limit. And as I pointed out, the grey area there, high standing submerged continental crust. And beyond that grey area is a quick drop off to extensive oceanic crust of, I guess, the Pacific and Australian plates. Justin spoke briefly about Nick Mortimer. There's a lot of geologists around who've been working to have this recognised, and throughout we've got quite a few little resources or links that take you to see some of Nick's work. So, yeah, really broad New Zealand, and a lot to explore, particularly across the different districts in New Zealand.
Okay, so if we start looking at specifically the geological history of New Zealand, I think to understand how New Zealand's developed, or Zealandia's developed over time, you really need to understand how the nature of the plate boundary has changed. So if we go right back 300 million years, Zealandia was a part of Gondwanaland, the supercontinent with Australia and Antarctica. And there was, and still is, running down the east coast of Australia and down into Antarctica, there's a large mountain range. So that mountain range was undergoing significant erosion, and that erosion was running down oceans and into the ocean, running down rivers even into the ocean, just like what's happening on the east coast of the South Island at the minute. And that deposition built up layers in the ocean of sediment around where New Zealand is, or around what is now New Zealand, I should say. So hopefully you guys have seen those jigsaw puzzles and things that we do with the continental drift, and that shows the Glossopterus and the different sort of dinosaur fossils on those different continents in similar areas that support that continental drift theory. So this slide here shows you a little bit better about that continental shelf and the fan of sediment that's eroding from the mountains, coming down the rivers and building up in the ocean. And over time, that sediment built up and lithified, turned into rock. And that's what formed the greywacke, which is considered to be the basement rock, which is found all over New Zealand. So it's like an old grey sedimentary sandstone that's found all over the place, and there's different grades of it. And what's also, so the sedimentary rock, that's good for the rock cycle. That also helped to develop the schist, and the schist is basically metamorphosed greywacke. So if you go back 2 slides, you could see that there was a destructive plate boundary, a subduction zone running down the edge of Gondwana, where Zealandia was located, and that meant that the greywacke on top of the oceanic plate was being subducted down underneath what's now Australia and Antarctica. And if you can have a look at where the accretionary wedge is on that bottom diagram, so the greywacke was being scraped off and buried to considerable depths, and there was enough pressure and temperature at depth for that greywacke to be metamorphosed into schist. I've seen a lot of misconceptions that the schist is formed in an accretionary wedge, but it's linked to the sort of the Hawke's Bay subduction zone, the Hikurangi subduction zone. But the New Zealand schist is much older than that, and it links back to Gondwana times, which is, if you have a look at a geological map of New Zealand, Otago is mostly schist, and then it runs up the Southern Alps as well, where it's come back up to the surface after the erosions.
So to support this, you can see the GIF image there changing, and it's describing the initial breakup of Gondwana into its present day setup. But we're still a little way from getting to that point just at the moment. So this is a 20 million year period, just as it started to break up. And one of the main reasons for that would be changes in mantle convection. It's possible you could teach this with your probably year 12 students. and this is what's referred to as Wilson cycles. It is the formation and breaking up of supercontinents. So there's been quite a few hypothesized supercontinents, but there's also evidence for a few others. One was Rodinia, and that predates the Cambrian, roughly 600 million years ago. The next supercontinent was Pangaea, roughly 300 million years ago. So convection within the mantle will open and close ocean basins, bring continents together before separating them again. And Pangaea 300 million years ago did separate into the Laurasia, the northern continents as we know them today, and Gondwana, which makes up the southern continents at that time. So yeah, on a long time scale, they open and close. Do note that in this here we see at about 85 to 50 million years ago is when the Tasman Sea officially opens up, and New Zealand is slowly peeling off the side of the Australian landmass. Next slide, please, Justin. And as we're trying to do, present a bit of evidence that supports these claims throughout as well. And one piece of that evidence is the KPG, or as you may have heard of it before, the KT boundary. So we're talking about the Cretaceous-Paleogene boundary. There is quite a significant layer of iridium. Now, while that, iridium, it's a pretty rare earth element. And all of a sudden, there's a huge amount of it in multiple locations across the planet. Now, while it's not critical to teaching geology, I've sort of included this evidence here to sort of highlight how the Earth system interacts with space. It's proposed that this iridium layer was created by a huge meteorite crashing into planet Earth around 65 million years ago. And, many hypothesize that this is what's brought the demise of the dinosaurs on. The top image in the slides there is from the South Island. I personally have never been to this site, but it's an extensive iridium layer found in the Southern Alps. What that shows us is, we can time it, as well as having connections to being connected to the other parts of Gondwana. It's found sandwiched between some deep water sedimentary rocks, and again, that alludes to our submarine origins. We have a few dinosaur fossils that are found across New Zealand. The vast majority of them are marine ones. And, that, again, marine dinosaurs, marine origins, but there are as well a few terrestrial dinosaur fossils that have been washed out from older sediments that are, showing that potentially parts of New Zealand were above the sea at the time. One thing I want to raise just before we move on, Justin at the start mentioned that one of the science standards about claims and evidence. Most people would say, yeah, the meteorite is why the dinosaurs are no longer here. I'll just point out that there's quite a bit of evidence to suggest that dinosaurs were already on the decline. And another cool theory supports that massive volcanism and huge amounts of carbon dioxide entering the atmosphere sort of predate the meteorite, and that's what sort of already had started their extinction. That massive volcanism has formed sort of kilometre-high lava flows in the India region. Some of you may have heard of the Deccan Traps, and I guess it's kind of significant. The demise of the dinosaurs could have been from massive carbon dioxide emissions, and that's very, very similar to what the Earth is experiencing today with human-induced change. And, we're seeing similar levels of species decline. The final thing I'd point out too, that with our submarine origins, essentially, there weren't too many mammals hanging around New Zealand. And what that sort of drove was, diversification and, isolated evolution of New Zealand's quite common ratites or flightless birds. And the reason for that would have been the absence of mammalian predators. So quite a lot of evidence that links to sort of us being underwater roughly 60 million years ago.
And this goes back to I think Mike was mentioning at the start with the drowning, the Oligocene drowning, which is, if you say that to a geologist, they tend to get their hackles up and start looking for an argument. I mean, there is discussion about how far or how much of New Zealand went underwater 25 odd million years ago. What we do know is that because the Tasman Sea was opening up, that put stretching forces on the plate, on the continental landmass of Zealandia, which made the crust stretch and thin, and that's why a lot of the continental crust was pulled down under the ocean. That formed a lot of the limestone that you see all over New Zealand, really, because it was a shallow sea that wasn't really associated with any sort of sedimentary runoff from a continental landmass. That meant that limestone formed in many places. So the limestone in New Zealand, they say, was mostly made up of things like bryozoans and foraminifera. I can never say that one properly. And that built up layers and layers of limestone over millions of years. And then again, when the nature of the plate boundary changed again to being destructive, moving towards itself again, then all of that limestone, or a lot of that limestone, has been lifted up above the ocean. That's where things like the Waitomo caves and Takaka, Oamaru, Whitestone, all those limestones all over the country came from that Oligocene drowning kind of period.
And just a quick addition to the fossils that Justin's mentioned. If you do level 3, 3.3, I believe it is, the geological dating standard, limestone, if you've got it near you, there's going to be some fossil evidence, and what a great way to sort of apply one of those, as they refer to, cross-correlation of lines of evidence to support aging of the rocks. So, yeah, really recommend checking out some limestones if you have them nearby you.
The local geology department, the Otago Geology Department, has really good foraminifera sort of keys that you can use. And when we take our students down there, they get out the foraminifera fossils. You look at them under a microscope, and you can use them to date rocks really accurately, actually, for their age. So that's a really cool activity. I've been trying to develop for my own students in class as well, but it's one that's worth looking out for.
Awesome. Justin, if you could just make sure this video works while I talk to it.
Yep.
Yeah, just get it prepped in the background. So this is personally not mine. If you've ever been to the Auckland Museum, they have a fantastic volcanoes and earthquakes area. And this is from the Auckland Museum. So I'll just point out that after the Oligocene drowning, bit of another change in the plate boundary, the way it was operating, and New Zealand now moves into a pretty explosive period. It's from roughly 25 million years ago, and you certainly will know that we still have extensive volcanism. I won't do much talking as the video plays. I want you to hear what it has to say. But what it will do is highlight a bit of a migration of the major or larger volcanoes from, I guess, the west coast of New Zealand, and migration towards its present day location off the east coast. And a quick disclaimer: the volcanoes that you're going to see in the video, they're not to scale whatsoever. They're all roughly a similar size, but yeah, it certainly is. It certainly shows how the volcanics have moved around. So, Justin, if you could play that video.
Let me know when you can see it.
Can see it.
About 26 million years ago, Zealandia, the ancient continent of New Zealand, stretched and thinned by tectonic forces, had almost disappeared beneath the waves. What saved it from disappearing altogether was the renewed vigour of the collision between the Australian plate and the Pacific plate, which pushed the land out of the sea again. As the Pacific plate was forced under the north of New Zealand, a belt of volcanoes erupted in what is now Northland, moving southwards over millions of years towards the Coromandel. Off the west coast of Auckland, the huge Waitakere volcano rose from the sea floor, its summit emerging out of the waves. Further south, the South Island was a subdued landscape, largely free of mountains and volcanoes. But this too was about to change dramatically. 13 million years ago, a hotspot plume broke through the Pacific plate, erupting where Dunedin is now. The first eruption centred on Port Chalmers, forming the lofty hills around Dunedin and Otago Peninsula. Then a string of smaller volcanoes emerged as far inland as Ranfurly. "10 million years ago, it was Christchurch's turn. A hotspot created 3 massive overlapping shield volcanoes, Banks Peninsula. 4 million years later, the action had shifted further east, as yet another hotspot brought the Chatham Islands up out of the sea in a series of blasts over 4 million years. Meanwhile, in the North Island, volcanic activity had been moving south and east as the Pacific plate began to dip down more steeply under the Australian. One result was the creation of the most active and violent volcano in New Zealand, Taupo. And further north, where it all began, 250,000 years ago, Auckland began to blow again, driven by another hotspot under the Australian plate.
Awesome, thank you, Justin. As I pointed out, they certainly weren't to scale. The Auckland volcanic field there, the image was showing about a similar size to the Taupo eruption, which you may be aware of was extremely destructive and potentially going to blow its top again at a much larger scale. Justin, if we could have the slide up again, the next one, thanks. Yeah, awesome. So this here is we're just gonna dive into the explosive history a little bit more now by sort of differentiating the different types of volcanoes around, and the first part of that would be looking at subduction volcanoes. As I've initially pointed out, we've got oceanic and continental crust collision, and the plate boundary has been migrating and establishing over the past 30 million years around. This particular image, you'll see a hyperlink below. That book is free, and I really recommend everybody to download a copy of it. It's no longer in print, so it's free. And it's by Bruce Hayward. Many of you may have heard of him, but he's been all over New Zealand and writing about geology, particularly volcanics and the fossils found for over 50 years, essentially. I think he did his PhD in, it might be 1978 or something. So he's extremely knowledgeable. Bit of a grumpy man. I hope he's not here listening, but yeah, pretty standard geology type. So the book is incredible. It's got so many great pictures and great diagrams like so. And what I want to point out here is the ages of the volcanic belts. So I'm just starting off with the pink regions. We've got the Northland Arc and the Eastern Belt and the West Belt. It's split into two. So one of the volcanoes mentioned in the museum video was the Waitakere volcano. I know a bit about it because I'm up here in Auckland and we use it as a field trip site. Probably about 10 times the size of Mount Ruapehu, but due to our submerged history, much of it's disappeared. And if you're in or around the Auckland region, the vast majority of the Waitakere ranges is eroded deposits from that volcano. Moving east, as the subduction boundary develops, volcanism, it ceases in the northern region about 15 million years ago. And at that same time, it started to develop in the Coromandel Peninsula. Again, heaps of volcanic features there, and much of the ranges itself are volcanic deposits. Now we're at our present day, which is our yellow TVZ or Taupo volcanic zone. Only been active for about 2 million years and still active today. And what you can see there is extension labeled between the Coromandel and Taupo volcanic zone. That extension thins the crust, it weakens it, it easily allows magma from our subduction zone to come up below. The Taupo volcanic zone, it extends offshore, connecting to also the active Tonga Kermadec arc, and that essentially runs all the way up to Tonga, about 3,000 kilometre volcanic range. And I might be wrong with the maybe start of 2022, connected to the same sort of volcanic processes. You had that giant eruption offshore in Tonga, which physicists say is the biggest sound ever created. There's images of a sonic boom across the country. So I guess I'll just mention, because I know someone had asked a question about the Auckland Auckland sedimentary basin. So I'll just quickly touch on that as well. And that was, if we look at the timing, ending about 15 million years ago, New Zealand has now moved out of its Oligocene drowning phase, and we're starting to, through volcanism as well, become a bit more buoyant and be thrust up out of the ocean. As a result, there was extensive erosion taking place, particularly in the Waitakere volcano. As I mentioned, it's just volcanic remnants now, but that extensive erosion led to massive deposition of sediments in the Auckland area, and what that has created is the Waitemata Basin. If you've been around Auckland and any of the beaches, you'll notice consistent alternating sand and mudstone layers, and that's all volcanic origin sediments that have come from the Waitakere volcano. And if there's sedimentary basins anywhere near you, a lot of it can also be attributed to the lifting up of New Zealand out of the ocean and high amounts of erosion taking place.
Yeah, I think Ross has covered a lot of this, but this is classic kind of level 2 extreme earth events standard. If you've done that, you should be pretty familiar with this. But this is the current situation of the plate boundary in the North Island of New Zealand, with the thinner and more dense oceanic crust subducting down beneath the thicker and less dense continental crust of the Australian plate. And then you can see as that happens, the oceanic plate melts, adds a lot of heat and a lot of gas and a lot of water to the into the kind of upper mantle, I guess, lower crust. And then that comes up and causes a lot of that volcanism in the Taupo volcanic zone that's going on. And as you said, as that happens, that kind of catches on the edge of the continental crust and pulls that down, which is causing that stretching, that extension of the North Island as well, which causes a lot of kind of earthquakes and fault lines in that as well. Anything you want to add about that one, Ross? Closer to you.
I agree with what you said, and I guess the Hikurangi subduction zone. It's quite specific to just offshore the sort of Hawke's Bay region. Subduction, as I pointed out, does occur all the way up to Tonga. I'm not 100% sure on which point they sort of changed the name from the Hikurangi subduction zone to the Kermadec Trench, where the same processes are happening to still produce similar types of volcanoes. The key difference, I'll sort of get to that on the next slide, but the key difference as well between the Hikurangi and Kermadec Trench is that the Hikurangi has continental crust, so it's a bit harder for the magmas to migrate up to the surface. And offshore in the Kermadec Trench, while some of the volcanoes do make their way above the sea level, we end up having, I guess, slightly different eruptions due to the different chemical input. Which leads us to the Taupo volcanic zone. And before I do that, I'm seeing Katie's comment. Yeah, water in subduction zone. It certainly lowers the melting point of magmas. We've got a lot of saturated sediments. If you go back, don't do it now, Justin, but earlier in the slide, there was an image which showed the accretionary wedge as well as a trench. Sediments that are rich in silica, they're washed off the continent, collect in the deepest parts of the ocean, generally those trenches, and those saturated sediments then do help initiate melt, sort of shallow it in the crust. So the Taupo volcanic zone, if there's signs of an eruption and you live in the North Island, leave. There's a lot of evidence to sort of show that these are, I've seen the term used frequently across the world, but supervolcanoes, extremely dangerous, and much of that is due to the magma type that is produced. And so I guess a quick note, magmas, they're quite differentiated by their silica content, and what that does is change their viscosity. So a rhyolite magma, which leads to, as indicated on this slide, ignimbrite rock. It's extremely viscous, and what that means is gases have a pretty hard time escaping. So if those gases remain trapped in the magma, a lot of pressure builds up. Once the top's blown, it can really cause huge eruptions. Picture shaking up a bottle of fizzy drink, really, really strong, and then letting the top off. That's sort of what we're going to experience with future Taupo eruptions. There's a long history of them,
last one erupted in Taupo around 232 AD. That's a really, really good event to do for the geological dating in level 3. If you're new to teaching Earth and space science at level 3 and you want to do the geological dating one, I'd recommend going to this one first and foremost, because there's lots of information about it. You can see marked in the map there's the buried forest, and there's all sorts of tree ring data, and there's radiocarbon dating. And another one that I always talk to my students about, which is quite interesting, is there is records in both China and Rome of the Taupo eruption because of weather patterns and really nice red skies in the morning and the evening for I think it was several weeks, in fact. So that's a really good one to do for the geological dating for linking the systems around as well. Also links in really well with the atmospheres, I guess, as well, with the volcanic aerosols and things.
Yeah, I've read somewhere too. There is ash deposits in Japan as well. A strong correlation to not only the chemistry of the ash that's here in New Zealand, but also the time as well. Just before we move on from this, I'm not sure Lucy from Tauranga Girls had asked a question in advance about rhyolites in the area. And it was about dome formation. So I had mentioned that rhyolites are extremely gassy, which lead to very explosive eruptions. But the domes form, I guess, after the really large explosive phase.
So a lot of the pressure empties out from the magma chamber. The magma chamber is full of gas, and that blows the top. And then the volcano stops erupting, and the magma chamber has a lot less pressure in it. So the crust actually sinks back down into the magma chamber, and that forces some of the degassed rhyolite out, and that's what forms your lava domes, like Mount Maunganui, I believe, is one, isn't it? If you go up to Rotorua, you can see there's one in the middle of the lake and all around the sides of the lake. Anywhere around the caldera, there's going to be lots of lava domes as well.
Yeah, quite frequently the domes are kind of the last remnants. I like to sort of pitch it like the toothpaste is running low in the bathroom, but you've got to squeeze the last little bit of toothpaste out. It takes a lot of pressure and it just sort of holds its shape. So sometimes that magma is coming out of the main vent and it just solidifies, and rhyolites are pretty resistant to erosion. So those dome features do last a long time.
Ross, just got a question from Najine in the comments. I think she's talking about the sandstone linked to the Waitemata or Waitakere volcano, Waitemata sandstones. Would that be from subsequent erosion after the eruption, or is that linked to the actual volcano?
Najine, what I know of is that they, again, trying to link chemistry of the rocks together, is that a lot of the sands and muds in the Waitemata sandstones have a very similar chemistry and origin to what the Waitakere volcano, what the Waitakere volcano shows. And so it would be from erosional events of the initial eruptions, if that makes sense. I don't know, type a few more questions away around that, and I can get to that after I finish this little part as well. One thing I do want to highlight about the Taupo volcanic zone is it is pretty complex. It erupts basalts, it erupts andesites, dacite, and rhyolites. And, typically, as we'll see when I talk about intraplates and basaltic volcanism, that's a bit ironic, but all I would say at this stage is some of that geology idea is probably well above what we would want to be teaching our level 3 students. And there's a couple of reasons for the differentiation in magmas erupted there. The thinning crust, some magmas can easily get through, but there's also a couple of other higher level things like partial melting and magma differentiation.
There was a question about Mount Tarawera quite a few years ago, I think, in the level 2 extreme earth events, and it was just too hard because it was talking about Tarawera, which is linked to kind of caldera erupting basalt. But what we've come to the conclusion with about level 2 is that we keep it simple in terms of basalts are linked to intraplate volcanoes, andesites are stratovolcanoes, and anything linked with a caldera is your rhyolitic, which is the high silica one. So basalt, low silica, rhyolite, high silica, and andesite, intermediate. And I think that's the level that you need to go to for your level 2 extreme earth events standard, really. Beyond that, it just bamboozles your students, really.
I mean, even bamboozling for an educator and non-geology specialist as well. So
very much.
I guess a key idea about the Taupo volcanic zone before we move on in its ability to create rhyolites is that it is continental crust in that region. So as magma is migrating up to erupt, it's capable of melting and incorporating a bit more silica from the surrounding crust. And we'd already mentioned too that subduction zones, they do add saturated sediments rich in silica. So we've got multiple opportunities for a simple andesite to change its chemistry and become far more viscous and far more explosive. All right. Next slide, please, Justin.
There's just a quick question about lava domes not being associated with caldera. Talking about the Tauranga volcanic zone has lava domes, but not caldera. Would that maybe be an older stage of the subduction zone when it was a bit further around?
I'm not 100% sure of that. Caldera, I guess we might sort of expect it to be an absolutely ginormous sort of lake, but sometimes calderas can form on a much smaller scale. And I do know that around the Tauranga region, I'm not 100% sure of the name. It's on the Tauranga side. There's quite a large lake, and in the middle there's a small island where it's actually a cemetery for one of the local iwis. Even that in itself is a small caldera. I think it might be only about 3 or 4 kilometers in diameter. But, that still goes through the same formation process. Large explosive eruption and a bit of a collapse back in to form sort of a lake structure. So, sorry, I'm just reading the question now.
Yep. So there's a question from Nick as well. Can we predict the next TVZ eruption? I would say, I think that's probably going to be less predictable than maybe even, they reckon in Auckland, they should have a couple of days warning because they track those earthquakes coming up through the crust very carefully. And every now and then you'll see in the news that there's been earthquakes, maybe 3 or 4 Ks underneath Auckland, and they're tracking them in case that's a basalt sort of tube coming up towards the surface. I think, and I might be wrong, but I think with the Taupo volcanic zone, that's going to be much bigger and much more explosive. So there might well be less warning about that. But what I do know is I've read stuff recently about Yellowstone, which is another supervolcano, and parts of the crust in Yellowstone sort of suddenly bubble up and go down by even a couple of meters. So they kind of suggest that Yellowstone is more active than the Taupo volcanic zone and is therefore more likely to erupt in the near future, whereas the Taupo volcanic zone seems to be fairly stable in comparison. So fingers crossed we're quite safe. But then I don't think we know is the only answer. I don't think it's very predictable at all, unfortunately.
Yeah, pretty unfortunate. I'm aware there's a few other tools to sort of predict volcanism. I'll talk about Devora shortly, which is more local to the Auckland area. But I also know that sulfur dioxide emissions are carefully tracked for supervolcano regions, and also sort of ground.
Sudden changes in chemistry can indicate imminent eruptions, can't they?
Yeah. So, yeah, what you mentioned, Justin, is certainly true. Auckland is a much shorter time span for eruption predictability, whereas the Taupo region, there should be quite a few more signs. But, super volcano, pretty unpredictable.
I think the eruption previous to the Hātepe eruption was like 20,000 years ago, wasn't it? And then the next one was like 232 AD. So hopefully it doesn't happen for another 20,000 years. I'm not sure about the other many sort of caldera around the area though.
Yeah, I'm pretty confident that GNS, who sort of track, they change the volcanic explosivity indexes as well as the the risk factors. They do use satellites and GPS to track ground deformation as well. In addition to strategically placed gas monitoring stations and water chemistry testing, all of that stuff would be what's used to sort of see the signs of impending doom, as I would refer.
The next time it happens, they'll probably be able to see what the signs were. But before that,
yeah. Awesome.
We click on?
Click on, yeah. Right, another part, intraplate volcanism, which was highlighted in the videos, much smaller volcanic features, but often a bit more numerous. And Auckland is a great place to explore this because there's there's been, I think, 52 or 53 identified. Certainly not that many of them still around due to, I guess, human influence. A lot of mining for aggregates and things like that in the Auckland region. But an intraplate volcanoes a lot smaller, and we would often refer to these as hotspots.
Can I just add in there, Ross, that the animated GIF on the slideshow, like most information about intraplate volcanoes, is relevant to Hawaii, which is and isn't sort of closely linked to the Auckland volcanic field. It gives you an idea of the hotspots, but I think Auckland's slightly different to that, really, isn't it, Ross?
Yeah, again, because of the continental crust below. But, as I mentioned before, with the migration eastwards of the subduction volcanoes, what it did was thin the crust. The Hauraki Plains is a great example of that. And the thinner crust allowed magma from far deeper below to actually end up getting to the surface. It's pretty periodic. And, I've mentioned here, it's over the last 10 million years that it's been happening across New Zealand. But Auckland, it would be one of the youngest sort of intraplate volcano features around.
I know Dunedin still does have an active magma chamber underneath it, but it will not erupt again because the plates are now pushing towards each other and they've thickened to the point where the magma won't won't get through the continental crust anymore. At least that's what the geologists at Otago are fairly confident about. So,
oh, great, yeah, Katie, as you pointed out, the Hawaiian island chain, they are, well, not even just the biggest volcanoes, but if you measure it from the seafloor to the top, it'd be the biggest mountain in the world. I think it would be sort of from summit, which is probably 4 kilometers above sea level, down to the ocean depths, probably makes it about a 10-kilometer high mountain. So they're forming in the same way. And I couldn't find a specific Auckland image, but the GIF here is showing magma rising and the plate migrating across the surface. Closer to New Zealand, if you've looked at bathymetry maps, you'll see the same sort of island chains forming. We've got offshore beyond the Chatham Islands. It's referred to as the Louisville Seamount chain. Plenty of that happening across New Zealand. And on the next slide, we can see just where those intraplate volcanoes have been. So we've got them scattered across both the North and South Island. You can see on the left-hand side, the Auckland volcanic field being the youngest. Further south, the South Auckland volcanic field around the Waikato region, I would say. Excuse me, erupting about 1 million years prior to that, but also far further north. If you're up there, there's so many hidden volcanic features, as well as extending out off to sort of Great Barrier in the Mercury Island region. They are all erupted in the last 10 million years. And switching over to the South Island, the video before mentioned Dunedin and Banks Peninsula. I think between about 10 million years for Dunedin, Banks Peninsula was about 4 million years, I believe.
The Dunedin one actually dates as far back as 16 million years and finished at about 9 million years ago.
Oh, okay, awesome.
We've done that one to death in level 3.
I think too, looking at the chemistry, the video mentioned as far inland as Ranfurly, and what's shown here, the Alpine Dyke Swarm. There's a lot of similarities in the chemistry of the magmas to the Dunedin volcanic complex as well. So, yeah, certainly a long history with intraplate volcanism as well. And, you know, Auckland being the youngest and more active, there's certainly a lot going into predicting the next location for its eruption as well.
Might want to just keep talking for a second, Ross, while I queue up the next video.
Oh, okay. Yeah. And what else I got to? I'd mentioned smaller eruptions. You know, we were talking about viscosity of magmas, with basalt being a lot less viscous. Gases can escape a lot more easily. So they're not as explosive and destructive as your larger topor eruptions. And that North Island image as well, that's come from that Bruce Hayward book too, which I've got the link present there too. What other thing can I point out? Yeah, Nick, with your question before too about predictability, still a real grey area for earthquake on the Alpine Fault too. You know, so I can't really truly answer whether or not there'll be a super eruption in Topor or a mega thrust earthquake, as they're referring to it as, along the Alpine Fault first. But the signs are there's a lot of worry for movement along the Alpine Fault.
Okay, so this is a really good, I think we're starting to look at the change in the plate boundary, especially in the South Island now. So this is a really great video for showing how the South Island especially has changed over the last wee while. Hopefully you can all see that. So there's a lot you can take from that video. It kind of demonstrates really clearly what's brought Zealandia back up out of the ocean after that stretching and thinning period. It also shows like the Southern Alps are only 5 million years old. They're very, very young mountains that are still being actively uplifted, and that's causing a lot of erosion and weathering going on at the same time. What else comes there? If you have a look at a geological map of New Zealand, there's some really good evidence, and there's some, I think it's granite mountains right up in Nelson. I'm not sure what, and then the same mountain chain of granite, the same rocks actually continue down in Southland on the other side of the Southern Alps. They're about 800 to 1,000 kilometers away from each other, and that represents the movement in the last 20 million years of that alpine fault and just how far it's come. Which is always blows my students' minds when you show that how far those mountains have moved in geologically a relatively short period of time. There we go. So this is a really good image as well that shows you because the Pacific plate, which is soft sedimentary continental crust, is pushing mainly past the Pacific plate along the alpine fault. It's also pushing towards at the same time, which is causing mainly the Pacific plate side of the alpine fault to buckle and fold and get pushed up above the ocean and right up. And they reckon if there wasn't for the erosion that the mountains would be about 20 kilometers tall, but over the last 5 million years there's been at least sort of 15 kilometers worth of erosion. And if you have a look at that sediment breaking down and washing across the South Island through all the big rivers like the Waitaki and the Clutha, and washing out into the ocean, and then basically ending up off the coast of the North Island, off the east coast of the North Island, a big kind of fan there as well. So there's really good rock cycle processes going on there that you can talk about too. I'd also flag a plug for the AF8 website, which has got some really good research in terms of, again, geological dating or a lot of those standards like the extreme earth events. There's really good research looking into how often the alpine fault has ruptured, and they reckon that every 300 years or so it goes laterally about 8 meters and does like an 8+ magnitude earthquake. And the last significant sort of earthquake on the alpine fault was about 305 years ago. So 300 years plus or minus 50 years, we're overdue by about 5 years, and an 8+ magnitude earthquake on the alpine fault. And they've even got models of if the alpine fault ruptures, first of all, in the south and the middle of the north, and they show you where the waves travel. And often they kind of travel up the alpine fault towards Christchurch and Wellington. So in most of the models, we're pretty safe down here in Dunedin, which I'm quite happy about. But the research of that, and also how they're preparing for that, is really good kind of socio-scientific issue stuff for the level 1 or 2 or 3 kind of standards for those ones. I'd recommend going and having a look at those.
AF8 as well. It's great for if you've got any, but self-managed students, they can do. There's some great student modules there as well with a few quizzes and things like that to help support preparation for that level 2 extreme earth events external. Really good resource for that also.
The Devora is a similar kind of socio-scientific one. You mentioned that before, didn't you, Ross?
Yeah, Devora is listed as one of the website links in the end, but Devora, it's an acronym for Determining the Volcanic Risk in Auckland. Long story short, a lot of PhD students at the University of Auckland in volcanology, that's what all their research is into. And, a lot of cores across the place, a lot of interpretation of the tephras, and just a good study of the 50 features that are around. And they've got some really good resources and publications that you could explore. If you're in the Auckland area, that would be a fantastic place to start off with planning a field trip. So yeah, I really recommend that. And I'm pretty sure it's, there you go. Thanks, Laura. Devora do great outreach also. Yeah.
Cool. Okay, that brings us to present day New Zealand. And you can see there how the plate boundaries are moving relative to each other, about 40 millimeters per year of movement in the south and about 50 millimeters per year in the North Island. And that, like the Alpine Fault, to be honest, I'd rather that ruptured sooner rather than later, because the longer it goes without rupturing, that means there's more tension built up in the fault, and that means there's going to be a larger earthquake potentially. So letting it go soon would be better than leaving it for another 50 years, really, of build-up.
Yeah, and also, well, that's kind of the real worry for the South Islanders. But subduction in the North Island too, it still poses significant risks for earthquakes, and alongside that, potential risk for tsunamis too. So a lot of evidence across New Zealand for historic tsunamis. Our most recent one was about a 1 meter high wave channeled through one small bay in the northern region that was linked back to that Tonga eruption. So I guess the whole of New Zealand's at risk of tsunami because we're an isolated island in the middle of the Pacific. But for North Islanders, the more significant risks are those volcanic eruptions. Whakaari claimed the lives of roughly 30 people a couple of years ago. Ruapehu's been quite an active volcano over the years, or that area anyway. And we've got some certainly worrying things, but geology. We've got amazing geology, and that's because of this very active plate boundary that we straddle. So a bit of concern for the future. And that brings us to where Te Reo Māui, or Zealandia, is heading in the future. So just put together a couple of little ideas. Those eruptions and earthquakes that we're concerned about, they are certainly going to be a lot sooner than Te Reo Maui's significant changes. But there's quite a few things that are going to depend on what the continent looks like in the future. So we've got continued weathering and erosion processes. That's non-stop. It will always be happening. It will always be changing the shape of the land. But a significant thing noted in the second bullet point, climate change and sea level rise. As that happens, the weathering and erosion is going to increase in its speed as well. We've got the large volcanic eruptions to be concerned about, and the large magnitude earthquakes in the Alpine and or Wairarapa fault regions. Another key thing to link back to, I'm talking well down the line, is the formation of a new supercontinent. And, because we're an isolated landmass and we have largely submerged continental crust, it's kind of predicted and modeled that as the next supercontinent forms, Zealandia will be left standing by itself. Australia is going to be neighbours again with sort of Asia and the Africa region, but Zealandia is just going to be sort of by itself out in I don't know if it would be called the Pacific Ocean anymore, but that supercontinent's it's sort of labelled as Pangaea Proxima, the next Pangaea. Bit of modelling shows we're going to be still happily just by ourselves in God's land, essentially. Yeah.
Okay, we're going to round it off in a second and finish off with the karakia, but towards the end of the slideshow, which we will send out, there is a link to a feedback form, and please, can everybody make sure you do the feedback form, which helps to justify more PD sessions like this, which would be great. There's also a bunch of links to standards, and there's also a bunch of URL links to websites and resources that we've used producing this, and we often use in our teaching as well. So anything else, Ross, before we move on to the karakia?
No. We'll just do a karakia and then have a quick chat about what is left on the resources and things like that if people are keen to hang around. So ka whakairea te tapu, kia wātea ai te ara, kia tūriki whakataha ai, kia tūriki whakataha ai, haumie, huie, taiki e. So there you go. Restrictions moved aside. Head back to whatever it is that you were doing, or probably leave the office and head home. Justin, if you could just flip to that last slide or two.
So I've just put the webinar evaluation link in the chat as well, if you want to get it from there, but we'll be sending it out with links to the recording and things as well.
And yeah, one of the last ones here, I just tried to put together how we can use what you've seen today to connect to a wide range of the ESS standards. And, you know, certainly 2.3 and 2.5 from the level 2 standards, as well as a big one would be the 3.3 or geological dating standard from the level 3 course. But, you know, even at the socio-scientific level, level 3, can an eruption affect me? How's it going to affect New Zealand? All of those sort of things are really key ones. And yeah, I think I've made a plug there for the regional reps. Don't be shy to ask for support from them. That's what we're here to do, but also GNS, tertiary providers, and that GeoTrips website that I pointed out at the start. Great places to begin.
I think we've got regional reps in every area around New Zealand, and we're all working really hard to make those connections with local schools. So if you can reach out to them, if you need moderation done, anything like that, just reach out and use us, because that's what we're here for.
Oh, Justin, you might want to...
Yeah, I'll fix that, Najeen. Thanks for that.
Yeah. And I think there's one more slide as well, Justin, maybe.
Yep.
Yeah, and the last one here, team, just a few hyperlinks for some of the more key things that we talked about throughout. So GeoTrips is there. A bit of Mataranga in that first article about how Te Reo a Māui was, how the name was given. So there's your sort of culturally responsive teaching link there. And we've also got Tiara, which is a great website regardless, as well as a link to the Out of the Ocean into the Fire book, another bit of Mataranga Māori for the Alpine Fault area, the What's on Our Plate module, and a link to Devora as well. So, yeah, I guess just from me, thank you for attending. I think the evaluation form is going to have a chance for you to leave some further questions if you feel we've left anything unanswered. And yeah, thanks very much for your time today. And we appreciate being able to share what we know with you. So yeah, thank you.
Yeah, thank you. Stop recording.